let's continue our discussion of the basics of quantum mechanics for quantum computing. So today we're talking more about measurements, quantum measurements. So we'll explore this idea of the collapse of the wave function in more detail, kind of getting the state after performing the measurement. And we'll discuss two extensions. So one is the notion of a partial measurement, where you have a system of multiple qubits and you just measure some of them. And then we will also talk about measurements in other bases, which are in general linear combinations of the computational basis we've been talking about. So let's start by reviewing the picture we had. So let's go back to 1 qubit. And the idea was that in general, you can have a state that's a superposition of 0 and 1. And we said physically there's some observable that we can measure. For example, it could be the direction of the angular momentum of a nuclear spin, and it could be either up or down, and we call one of them up, one of them 0, one of them 1, or it could be the direction of the current in a loop. So we assign these basis states to measurement outcomes, and we had then this idea that if we perform a measurement, we find one of these, and that transforms a state to one of the basis states. So consider a measurement in the computational basis (0 and 1), basis represented by these two vectors. So let's think about the fate of the state. So we essentially constructed these states as states corresponding to what you would get, after a measurement, and then we said the general state can be a superposition. So this implies that if you have this wave function, which is alpha 0 plus beta 1, let's say pre-measurement, this wave function goes to either 0 if we get 0 in our measurement, or 1 if we get 1. And that's post. So a measurement, the idea is that once you observe the system, you change its state. And this is called the collapse of the wave function. In other words, you have some wave function that's a superposition, and then it gets projected onto one of the basis states. So somehow the analogy with, let's say, 2D vectors in real space is useful. So imagine you have this x and y coordinate system, and you have some vector r. And so classically, well, the vector r is there, and you can always look at it and then nothing changes. Like suppose that's the position of some particle that's here. But quantum mechanically, if you have a state in a two-dimensional space for just 1 qubit, and if you make a measurement on this corresponding to this quantity that can be 0 and 1, right after the measurement, the vector gets projected onto one of the axes. So you essentially kill the component that would be inconsistent with that measurement result. And this follows from just an empirical experimental fact that, so experimental fact, if we measure a quantity and find a certain value, we always find the same value if we immediately remeasure the same quantity. So that's an important observation that allows us to generalize this idea to partial measurements in systems of multiple qubits. So again, this way we can understand the collapse of the wave function, because suppose you have this state alpha 0 plus beta 1. So we're saying if you have that state, the probability of getting 0 is absolute value alpha squared. Probability of 1 is absolute value beta squared. Now, if I measure in computational basis, and get 0, this observation implies that immediately after the measurement, the probability of getting 1 in a second measurement is 0. So that means beta must be 0, right? If you have any finite beta, there's a finite probability of getting 1. So if beta is 0, essentially alpha must be 1 up to a phase because the state is normalized. So this explains the collapse of the wave function, and the wave function similarly collapses for multiple qubits. So suppose I have, let's say, 2 qubits. So suppose I have, again, state that's alpha 0, 0, 0, 0, alpha 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. And if I perform a measurement on 2 qubits, so simultaneously I measure in the computational basis, again, the observable that gives me these zeros and ones, the wave function collapses to 0, 0 if we measure 0, 0, 0, 1, 1, 0, and 1, 1. So again, this means, if you measure 1, 1, then if you immediately perform a measurement on both qubits right after that, you're guaranteed to get 1, 1. So all of these other guys, 1, 0, 0, 1, 0, 0, if they're non-zero, that means there's some probability of getting those results. So we don't have a probability of 1 of getting 1, 1. So that's the idea of the wave function collapse. Now, let's consider a more more complicated case where we have a system of multiple qubits, but we perform the measurement on a subset of those qubits. So suppose you have 2 qubits, you perform a measurement on 1, or you have 3 qubits, you perform a measurement on 1 or 2, not on all of them. So let's talk about partial measurements. So again, let's give an example. So suppose we have 2 qubits, A and B. And let's say I have some state that's, let's say, written as, let's say, psi as an example. So suppose I have 1 over square root 3 times 0, 0 plus 1 half, let's say 0, 1. And let's say I have 1 more basis states. So so this squared is going to be 1/3. This is going to be 1/4. Their sum is 7 over 12. So let's say I have square root of 5 over 12, 1, 1. Right? We can check that the state is normalized. Because so they're real. I don't need to worry about the absolute value. This is 1/3, 1/4, 5 over 12, which is 4 over 12 plus 3 over 12 plus 5 over 12. That adds up to 1. Okay, so that's one normalized state. Again, the first one is qubit A, the second one is qubit B. So suppose we perform a measurement on qubit A. And get 1. Okay. So what should happen to the state? See, the state is a superposition of 1, 1. So 1, 1 is okay, right? If you perform a measurement on 1, 1 for qubit A, with probability 1, you're going to find 1. But any of these terms where A is 0, right? If you perform a measurement on them, they give you some finite probability of finding 0. So this should project the state to just 1, 1. There's only one basis state that's consistent with this measurement result. So this psi should go to just 1, 1 if we get, let's say, sigma A equal 1, the state of qubit A to be 1. We measure that to be 1. Now let's consider the case of getting 0. So what should happen? You see, the idea is that we want to make the minimal change to the wave function. So we have this superposition. We have 1/3, 0, 0, 1/2, 0, 1. And then there is this other term which has 1, 1. So no matter how you change, suppose you after the measurement, you change these coefficients in some way. So as long as you have any 1, 1, there's going to be some finite probability of getting a 1 when measuring A. So then when you get 0 for A, essentially we're killing this term, right? That has an A that's not 0. But there's one problem in that, because the resulting state is not going to be normalized, and the sum of the probabilities won't add up to 1. So then that gets corrected by just normalizing the resulting state. So partial measurements consists of 2 steps if you want to calculate the post-measurement state. So first I project out inconsistent terms in the superposition. So that gives me 1 over square root 3, 0, 0, plus 1/2, 0, 1. But then I notice that this vector is not normalized. So how can I normalize it? Well, I can just divide it by the sum of squares of these. So I can normalize here. All right, 1 over square root of a quarter, or 1/3 plus a quarter, which is a square, which is this quantity squared plus that quantity squared. And then I write my vector. So that's for sigma A equals 0 as a as a result of the measurement. So in general, let's say I have psi is equal to alpha 0, 0, 0, 0, alpha 0, 1, 0, 1, alpha 1, 0, 1, 0, alpha 1, 1, 1, 1. Then if I want to see what happens to the state after the measurement, well, suppose, psi A is 0, then I have to get rid of these 2, right? Because then these are the states that give a finite probability for finding sigma A to be 1. The first qubit has a 1 in that superposition. So in this case, my state should go to well, it first goes to this. And this is, of course, not a physical thing, right? This is just some mathematical way of deriving it. We first get rid of the ones that would be inconsistent with the result of the measurement, and then we normalize. But of course, in nature, the quantum state directly goes from a normalized state to a normalized state. It never becomes unnormalized, right? The state that's not normalized means there are probabilities that don't add up to 1, and that's not physical. So that's just a mathematical breaking of the problem into 2 steps. Physically, it's just one shot. Okay, so now this, let's say, goes to that. And then, well, this is not normalized, but to normalize it, I just divide by the square root of the square root of the sum of these quantities, absolute values squared. So if I divide that by square root alpha 0, 0, absolute value squared, plus alpha 0, 1, absolute value squared, you will see that this state is normalized. So let me write it as, alpha tilde 0, 0, alpha tilde 0, 1. where alpha tilde 0, 0 is just alpha 0, 0 divided by this square root. And alpha tilde 0, 1 is alpha 0, 1 divided by that. Then the normalization condition is that 1 must be equal to alpha 0, 0 tilde absolute value squared plus alpha 0, 1 absolute value squared. You have these coefficients, we take their absolute value square, you take the sum, they should add up to 1. These are the probabilities. And this is relatively easy to see. So the denominator is a real number, right? Absolute value alpha 0, 0 squared, absolute value alpha 0, 1 squared. These are real numbers. They're non-negative, so, and they can't be both. Well, they can't be both 0 because we actually got a 0 for the state of qubit A in our measurement, right? If they're both 0, if initially neither of these terms are present in the superposition, so suppose you have these guys, then the probability of getting 0 is 0. So you're not going to find that 0 in the measurement. If you found it, then there must be some finite probability in the original pre-measurement state. Okay, so then that's a positive number, and it's real. So then squaring it just gets rid of the square root, and then the alpha 0, 0, we just find the absolute value squared of it. And then for this one, we have a similar story. So you see now, if I combine these, they have the same denominator. So adding these gives me the denominator in the numerator. So it becomes something divided by itself, and that's going to be 1. So that's our recipe for finding the post-measurement state if you find a certain outcome when you perform the measurement on one of the qubits, on the first one. Similarly for completeness, let's keep going with this. So if I now say I get sigma equal 1, starting with that general superposition, so what should happen is psi should go to now, I need to project out these terms that have a sigma equals 0. They would be inconsistent with that measurement result after the measurement. So I'm going to get these. So I project out, I kill these terms. I'm left with those, and then I normalize them. So I'm going to end up with 1 over square root of alpha 1, 0 absolute value squared plus alpha 1, 1 absolute value squared. And then what remains is so that's wave function collapsed in a partial measurement. And this story essentially continues. So you can have systems of more qubits and play the same game. So suppose, let's do another example here. Suppose I have 3 qubits, and let's say my state is 1 over square root 3, let's say e to the I pi over 4 times 0, 0, 0 plus 1 over square root 3 times 1, 0, 1 plus 1 over square root 3 e to the minus I pi over 4, let's say 1, 0, 0. And then, so again, let's say this is qubit A, this is qubit B, this is qubit C. And suppose we do a measurement on qubits A and B. We don't measure C. And find 1, 0. Right? So we measure the first 2 qubits, we find 1, 0. So what is a post-measurement state? Okay, so I look here. So the first one has 0, 0. So that's out, because if this term remains in the superposition, it gives a finite probability of getting something that's not 1, 0 for the first 2 qubits. This one is good. It has 1, 0. This one also has 1, 0. So first my psi goes to 1 over square root 3, 1, 0, 1, 1 over square root 3 e to the minus I pi over 4, 1, 0, 0. But then we notice that this is not normalized, right? So the absolute value squared of this is 1/3. The absolute value squared of this coefficient is also 1/3. So if this is, let's say, alpha 101 is 1/3, is 1 over square root 3, which means 101 absolute value squared is 1/3. And then alpha 100 is 1 over square root 3 times some phase factor. Again, the phase factor goes away when I take the absolute value, because you multiply that by its complex conjugate. So we multiply e to the minus I pi over 4 by e to the plus I pi over 4, they go away. So that gives me, again, alpha 100, absolute value squared is 1/3. So now to normalize this, I have to divide by the sum of these two things, which is going to be square root of 1/3 plus 1/3. Then, of course, we can simplify. One, 0, 0. Okay, so that's a good example for a partial measurement. So I have a system of 3 qubits. I perform a measurement on 2, and then I find my state after the measurement that's consistent with the result of the measurement. Okay, so now let's talk about another topic. So these are measurements in a different basis. So let's go back to this picture that we started from, just real space vectors in some coordinate system. So again, so I have some coordinate system x and y. It has unit vectors I and j. And let's take some vector here, vector r, that has some component x and some component y. So I can write my r as xi plus yj. So then the idea is that that vector is just some geometric object, right? And the choice of the coordinates is up to us. So alternatively, I could have chosen some rotated coordinate system. So let's say take these and rotate them, for example, by 45 degrees. Then I have a different coordinate system. Let's call them x prime, y prime. And then they will have their own unit vectors. Let's call this I prime, call this j prime. So let's redraw that. So just so the figure is easier to see. And I have this vector r here. So again, I can write the components of r in this new coordinate system, right? I can go from here to here. Let's say this is I prime, this is j prime. So from here to here, I can imagine some x prime that's going to be a different number. It's not going to be the same as x. And from here to here, I can imagine some y prime, such that the same vector r, is given, these are the same thing, by x prime I prime plus y prime j prime. So it turns out in quantum mechanics, we can play the same game. So essentially the 0 and 1, which correspond to some measurements. So for example, it's like you take the spin or the intrinsic angular momentum in some direction, in the z direction. And that gives us two values. So we call them 0 and 1, and then they provide two basis vectors for the space in which the state of this qubit lives, the superposition lives. Now, we can take some linear combinations of these two vectors in such a way that they're still orthonormal. They still have length 1, similar to this. Here we have two unit vectors. And here the two are perpendicular to each other. Again, we can take two linear combinations that are orthogonal to each other. So that would also give a perfectly valid basis to write any state as a superposition. Now we can go backward, right? So we said that the result of the measurement provides a basis, but now we can transform the basis, rotate it if you wish in some way. So we get a new transform basis. And then it turns out that there's going to be other measurements. So these are measurements of other physical observables, like measuring, let's say, this angular momentum instead of the z direction in the x direction, in a different direction, such that the states after measuring these different observables are these rotated, transformed basis states. So the message is that there's a correspondence between basis states and measurements. So let's write that in words. So we're saying, first, we can transform basis states. So let's give an example. So suppose I have 0 and 1, and then consider 0 prime to be 1 over square root 2, 0, plus 1 over square root 2, 1, and consider 1 prime this is just an example, of course, to be 1 over square root 2, let's say 0, Oops, I already factored out 1 over square root 2, so I don't need it here. Plus 1 minus 1. And we can check that, so here the property was that we had 0, 0 was equal to 1, 1 was equal to 1, right? One way to think about that was that the representation of 0 in the 0 basis is just 1, 0. The representation of 1 is just 0, 1. And these guys, and also, of course, then 0, 1 is 0. They're orthogonal. So here, let's represent these in the same basis. So this is going to be 1 over square root 2, 1 over square root 2. So it's clearly normalized. So 0 prime, 0 prime is 1. That's fine. This is going to be 1 over square root 2 minus 1 over square root 2. Again, 1 prime is 1. And I can check the inner product of 0 prime and 1 prime. So that's going to be 1 over square root 2, 1 over square root 2 a row, 1 over square root 2 minus 1 over square root 2 a column. So that becomes 1/2 minus a half. It's going to be 0. So this is a perfectly fine basis. Any linear combination of 0 and 1, we can write as a linear combination of 0 prime and 1 prime. One way to see that is we can just solve these equations. So you can, let's say, add these. So I write 0 prime plus 1 prime is going to be 2 over square root 2, 0. And then the ones cancel out. And 0 prime minus 1 prime is going to be 2 over square root 2, 1. Now the zeros cancel out, the ones add up. So in the same way that, these are linear combinations of 0 and 1, 0 and 1 are going to be linear combinations of 0 prime and 1 prime. So that means 0 is 1 over square root 2, 0 prime plus 1 prime, and 1 is 1 over square root 2, 0 prime minus 1 prime. So now if I have any linear combination, suppose I have alpha 0 plus beta 1, I just plug in, right? For 0, I write this linear combination. For 1, I write this linear combination. I recombine the terms. So that seems to be alpha plus beta over square root 2 times 0 prime plus alpha minus beta over square root 2 times 1 prime. So any linear combination you have of 0 and 1, which is some arbitrary state for this qubit, we can also write as a linear combination in this new basis. Okay, so that's step 1. We can consider transformations to different basis states. Then there was this correspondence between 0 and 1 and measurement outcomes. So the idea is we can imagine for any orthonormal, in the sense that different basis vectors are orthogonal and each of them is normalized, basis, we can have measurements that project the state two basis vectors. So again, the result of the measurements in the computational basis, in the original basis, was that this guy went to a basis vector, got projected either to 0, if we get 0, or to 1, if we find sigma equal 1. Similarly, you can imagine performing a different measurement with respect to a different basis, such that the result of that measurement projects this vector onto this different basis. So there is a correspondence between and projective measurements. So let's go back to our example. So here, performing this measurement in the computational basis gives us 0 after the measurement if I find 0, and the probability of that is, of course, absolute value alpha squared, and the probability of getting 1 is absolute value beta squared. Now, we just wrote the same state, right, in a different basis. So let's call it alpha prime 0 prime plus beta prime 1 prime, where alpha prime is alpha plus beta over square root 2, beta prime is alpha minus beta over square root 2. And now, if I perform the measurement in this other basis, so let's call that variable sigma prime, which can take these other values. Well, what happens is I will get this basis vector, which is some linear combination of zeros and ones, not the same. If, for example, sigma prime happens to be 0, I put a prime to just indicate that this 0 is in this different basis. But of course, 0 is 0. Again, you would be measuring some angular momentum, and you either find +1 or -1. So today we talked about quantum measurements. So there were 3 topics. So we reviewed the standard measurement a little bit that we had talked about before. We made it a little bit more precise in terms of getting the post-measurement state, which is essentially projection to one of those basis vectors. Then we talked about partial measurements, so having systems of multiple qubits, and then performing the measurements on some of them. So we found this recipe of getting the post-measurement state, essentially, again, projecting out anything that's inconsistent with the result of measurement, gives finite probability of finding something other than the result we just found. And then that gets rid of terms in a normalized state. So it makes the state unnormalized. We have to take another step and normalize it by just multiplying the whole state by some number. And then the last topic we talked about was the fact that the computational basis is not a unique basis. In the same way that vectors in real space you can pick some coordinate system and just write the components in that coordinate system, and they're all equally good. They describe the same vector. A quantum state also, we can write it in a different basis. And the basis vectors for this new basis, again, live in the same space, so they have to be some orthonormal linear combinations of the original basis vectors. We did an example. This is just one particular example, so we can have different coefficients, as we'll see later. But for this particular example, we did it a bit more explicitly, and so we identified this new set of basis vectors. We argued any state that you already wrote as a superposition of 0 and 1 in the computational basis, you can write as a superposition of these new basis vectors. And we said that, well, there doesn't seem to be much of a difference between 0 and 1 and 0 prime, 1 prime. They're equally valid basis vectors to represent the state. So we had this notion that the 0 and 1 states come from some measurement. They correspond to the results of of the measurement of some particular observable. The idea is that this carries over. So any set of basis states, one can think of some or construct something to measure, which would project a state onto these basis vectors. So there is this correspondence between a basis and measurements, and then all the mathematical machinery just works out fine. Again, the coefficients in this new basis are the probabilities of finding values associated with these new basis vectors. And similarly, the wave function collapses. So similarly, there's this projection to the new basis vector. So we can think of measurement as essentially projection to some basis. So next time we'll start talking about Bell states and quantum teleportation. And this machinery that we've developed, essentially machinery of tensor products dealing with multi-qubit systems and also performing measurements, allows us to study a very interesting application where by just sharing an entangled state and performing certain measurements, you can send an exact copy of a quantum state from one person to another, from one experimentalist to another. All right, that's a good place to stop.